Hello, welcome back. This is EEE 41 Lecture 15, where we'll introduce BJT circuits. For this lecture, we'll cover a few bipolar junction transistor circuits, although we'll focus mostly on NPN-based circuits. For circuits with PNP, the process is essentially the same, but voltage polarities and current directions should be reversed. Some PNP examples will be covered in the problem-solving lecture. Our objectives for this lecture is to use BJT circuit models for circuit analysis and familiarize ourselves how BJTs can be used as a switch and bias for use in amplifier applications. Before proceeding, let's have a quick review first of the operating modes of our BJT. So we have noted previously that we have 4 modes of operation: the cutoff, forward active, reverse active, and saturation, and these are based on the biasing conditions of the 2 junctions within the device, although we'll only consider in this lecture cutoff, forward active, and saturation, since most of the time we are not designing our circuits to operate under reverse active bias, and in that sense we'll be focusing mostly on this portion of the plot right here. And we'll also note that this IV curve is based on the VEC or VEC of the BJT, but the current also actually changes with respect to the base emitter junction voltage. And specifically, this change in or dependency of the current based on the base emitter junction voltage changes approximately with this formula right here. And since this formula actually depends both on VBE and VCE, that's why we are giving using a family of curves to represent the IV curve of the BJT. But if we want to plot the current in terms of VBE or using VBE as the x-axis, then we'll have to assume some value for VCE. And since this is the equation for the forward active region, what we normally do is, or what we normally get is the current values in the forward active region and refer it to some current point in the IC VBE curve. Now take note of this 1 plus VCE over VA term, which essentially tells us that the current IC at the forward active region will increase linearly with respect to VA, because this is a multiplication factor in this expression. So if we actually consider this increase, although most of the time we want this to be just slightly increasing, then what we'll get with the IC versus VCE curve is some slightly increasing linearly current. But to simplify things and to be able to plot the IC versus VBE curve, then we normally refer to this point right here. And also, if we assume that VA approaches infinity, which is the ideal case, then this term actually simplifies to just 1 and will be left only with this term, which tells us that IC increases exponentially with VBE. And so we get this plot right here. And so if we increase VBE linearly or with equal steps, then we'll get exponentially increasing collector current. So that's why these currents here are not equally spaced, even though VBE1, VBE2, VBE3 are equally spaced apart. Now for cutoff, we get that the current is approximately 0, and that actually um, is at this point of the curve. Now for saturation, for example, for the same VBE, say VBE3, this is VBE3, we get a slightly lower current than the current at the forward active case. So to plot the currents at saturation in this ICVBE plot, then we'll actually get something of a smaller current for the same VBE, but we don't normally show that and just simply show this forward saturation case. Now, for forward active region, we also have this formula that we can use. So IB is equal to IC over beta, and therefore, using this equation, we can just scale this down to get IB. In this slide, we outline some steps we can follow in analyzing BJT circuits, although you can deviate from this as you practice more or learn more how to analyze circuit. But if you don't know where to start, then you can follow this outline. First, you can assume that the BJT is in the forward active region or operation, and under this assumption, then we can use IC is equal to beta IB, and by KCL, since IE is equal to IC plus beta, IE is equal to IC plus IB, then this is IC beta IB plus IB. So we can use these equations. And since we are assuming the forward active case where the base emitter junction is forward biased, then we can assume that VBE is approximately VBE on. If we are not actually trying to compute the exact VBE, or if we are not given the exact VBE value. Now, after assuming the forward active case, the next step normally is to solve for IB. And this is normally done by writing an equation that involves the base emitter loop, so that we'll be able to determine IB. So for the case of an NPN circuit, so we have here our NPN BJT, and since we are assuming that it is in the forward active, or VBE is approximately or equal to VBE on, let's say that is 0.7, then we'll have this value right here. Then to solve for IB, we need to include it in the equation. So we'll use this IB right here and use, for example, the resistor connected at this point, or the bias voltage connected at this point. And either we do a KCL with that, with IC and IE, or we do a KVL normally downwards, although we can also actually perform KVL back upwards. Now, if IB is less than 0, then the transistor is actually in cutoff, since we assume that this is forward biased, just like in our diodes, but the current turned out to be negative, and that cannot be the case. And therefore, if you get this result, then the transistor is not in the forward active region, but actually in the cutoff region. Then redo the calculations with all currents at 0, since at cutoff there is approximately no current. Okay, so the other path is that if you get that IB is greater than 0, then proceed to step 3. So either we go from here to here to here, or from here to here to here, and actually end the analysis. So if we are to go into step 3, we solve for VCE by writing a KVL equation in the collector emitter node. So VCE is right here, So we just make sure we write an equation involving this unknown VCE. And then if VCE is greater than VCE sat, which is normally 0.2 for silicon BJTs, then if it is greater than 0.2 or VCE sat, then the transistor is indeed in the forward active region. But if it is less than VCE sat, then it is not in the forward active region, it is not in the cutoff region, but it is in the saturation region, or the transistor is saturated. And in this case, we redo the calculations with VBE is equal to VBE on, and VCE is equal to some constant VCE sat, which is approximately 0.2. Now, note that in this saturation case, IC is not equal to beta IB. So we only use this IC is equal to beta IB equation in the forward active case. Now, to sort of summarize the models that we'll use for NPN, again, for the forward active, we can use IC is equal to beta IB, or IC is equal to alpha IE, where alpha is beta over beta plus 1. Now, to remember this, always remember that the IC is on the left side and is not, say, multiplied by beta or not multiplied by alpha. And circuit-wise, this just means that IC is current-dependent current source. So this here is IC, and that is represented in this circuit by beta IB. Now, for the base emitter junction, since we are approximating that VB is equal to VB on, then we can replace that with this voltage source VB on. Now, in some models, you can actually see that that VB on is drawn under instead of the left side, but whichever is the case, you can actually get the same set of equations using either of these two equivalent circuits. Okay, so just like in our diodes, when we say assume its operation, we need to check some conditions. And for our BJT under the forward active case, specifically for NPN, IC must be greater than 0 or positive. And this means that IB must also be greater than 0. Although sometimes IB is equal to 0 when beta is infinite, since IB is equal to IC over beta, which will approach 0 when beta is assumed to be infinite. So we'll just, we can still check these conditions just by checking the sign of IC. Now for VCE, we must check and verify that VCE is greater than VCE sat for NPN. Again, VCE sat is normally approximately 0.2 for silicon BJTs. Now for PNP, this same condition must be met, although the direction of IC is now different and also IB. But for PNP, what we check is VEC to be greater than VEC sat, where VEC sat is normally, again, around 0.2 volts. Now for saturation, we mentioned a while ago that VCE is approximately equal to VCE sat. So we replace that with this voltage source, constant voltage source model, and VBE is equal to VBE on. So we get this another constant voltage source, which is not quite surprising since for saturation, both junctions are actually forward bias. So they both act like for forward bias diodes. Although take note that this is not 0.7 since this is not VBC but rather VCE. And in terms of our IV curves, in the saturation region, we normally work around this range, and that is approximately at 0.2. Unless for your application you're expecting to be working on this range, then you'll have to slightly modify the analysis. But most of the time, we can use this model right here. Now, the conditions we check, since we both assumed voltage values, then we'll have to check current values. So first, IC must still be greater than 0, since the base emitter junction is forward bias, and also IB is greater than 0. So this is just the same, but the condition for the collector current is that it must also be less than beta IB. So strictly speaking, IC must be between 0 and beta IB. And if it turns out that IC is not less than or greater than beta IB, then we'll have to assume forward active. Now for cutoff, both junctions are reverse bias, so the currents are approximately 0. So we'll just replace everything with an open circuit. But what we'll have to check is that VBE must be less than VBE on. And otherwise, it's either we are in the forward bias or saturation. So now let's discuss some example. First, we'll consider an application where the BJT is used as a switch. So we can model the usage of this BJT as some switch which shorts the path towards ground and controlled by some input voltage. So note that we normally use NPN BJTs to short the path to ground and PNP BJTs to short the path towards the supply. So let's see how this BJT will be able to act like a switch. So let's consider first the given. First, we have a VCC of 5 volts, then RB of 1 kilo ohm, then RB of 1 kilo ohm, RC of 10 kilo ohms, and then VC SAT, which is the normal value for silicon, 0.2, VB on 0.7, beta is equal to 100. Now determine V out. If for the first case, let's say we have here V in is equal to 0 for this slide. Now note that we are given here an NPN BJT. We also note the terminals. So this is the collector, this is the emitter, and this is the base. And also shown is the current direction. So the arrow is towards this. So IE is downwards, IB is rightwards, and IC is downwards. So when Vin is 0 volts, so we have here this 0 volts right here, and we know that this junction here is also 0 volts, then most likely there will be no voltage drop in this case for the base emitter junction. That is enough to turn it on. Then most likely this BJT is in the cutoff region, since the 0 volts will most likely not be able to provide the 0.7 to turn this on. And for cutoff, since our model is that this is basically an open circuit. So IC is equal to 0. There is no current here. Therefore, there is no voltage drop in this RC right here. So this is 0 volts. And if that is 0 volts by KVL, VCC minus VRC minus Vout is equal to 0. So since Vout is right here with respect to ground, so we have this here. And also, if you are not yet too familiar with this notation, this supply right here can be imagined as connected to a 5-volt source back to ground. And so our KVL can be closed through the ground back to this point. So we get 5 volts minus 0 minus Vout is equal to 0. And we'll eventually get that since there's no voltage drop here, Vout must be exactly equal to 5 volts. Now, since we assume that this one is in the cutoff, how can we verify that it is in the cutoff region? So since this one is also open here, then there is no voltage drop in this RB right here. Then we can actually say that VB is equal to 0. And since the emitter is grounded, then the voltage at the emitter must be 0 as well. And with these two values, we get VBE is equal to 0. And since this is less than VBE on, then we have just verified that indeed the transistor is in the cutoff region. And what we get is this Vout equal to 5 volts. Now going back to our application, BJT as a switch, then this just tells us that for this case, Vin is equal to 0, then the switch is open. And therefore, we get a Vout that is equal to 5 volts since there is no current flowing through RC. Okay, so what now if we have Vin is equal to 5 volts? So that means this one is at 5 volts and we have a 5 volts down to ground path, and that includes this VBE junction. Again, this is an NPN BJT, so we have this structure NPN, and since this is PN, then most likely with this 5 volts, this junction is forward bias. So the only way to analyze this is to assume forward active or saturation. But let's start with a forward active assumption, just like in our suggested flow. If we assume that it is in the forward active region, then we're constricting ourselves that this one is equal to 0.7 volts with this given. And we'll also defining IC, or we'll use IC to be equal to beta IB. So starting with IB, we have this. This current IB is the current through this resistor. So we use the voltage across the resistor over the resistance. So 5 minus 0.7 over 1 kilo ohms. So that is 4.3 volts over 1 kilo ohms. We get 4.3 milliamps. And from this 4.3 milliamps, we multiply by 100 to get IC, and therefore get 403 milliamps for IC. So the current here is 403 milliamps. And now VCE, which is, this is the collector, this is the emitter. So VCE is here, which is actually exactly equal to Vout. So VCE is equal to Vout is equal to 5 volts minus the voltage dropped through or across this resistor, which is RC, 10 kilo ohms times 403 milliamps. So this turns out to be this negative 425 volts. So let's just accept that value for now. And we have to note that this computed VCE is not greater than VCE sat. Okay? So negative 425 is actually less than 0.2, which is positive, and therefore we have not met the condition for forward active case, and therefore it is not in the forward active case, and we have to analyze it using our models for saturation. Now, redoing the analysis for the case of saturation, again, we're replacing the BJT with two voltage sources. So we have here 0.7 volts, and then this one here is 0.2 volts. So it is now easy to see that Vout is just simply 0.2 volts equal to VC sat. Now to confirm, we check IB. So IB is still 5 minus 0.7 over 1 kilo ohms, which is RB. Still we get 4.3 milliamps. If we solve for beta IB, this is 403 milliamps, but this is not IC. Okay, since we are assuming saturation. IZ, in fact, can be solved from KVL in this path. So IC is the voltage dropped across, or the current through RC, which is 5 minus 0.2 over 10 kilo ohms, which gives us 0.48 milliamps. Now, since 0.48, the actual IC is less than beta IB. This is much smaller than this one, and therefore IC is less than beta IB, and then indeed IC is within the range of 0 to beta IB, and therefore we can say that indeed the BJT is in saturation. So note that in the first case our output was 5 volts, and in this case our output is 0.2 volts. 0.2, 0.2, 0.2. This slide summarizes the results we've obtained. So for 0 volts, our output is 5 volts, and for a 5 volt input, our output is 0.2 volts. Comparing it with an ideal switch, in this case, when the switch is open, there is no current through RC, and we therefore expect our output to be equal to VCC, or the supply, which is 5 volts. So our BJT was able to replicate this behavior. However, for this case where the BJT or the switch is supposedly on, ideally the switch should be able to pull down the output voltage down to ground. However, our NPN BJT was only able to pull it down to 0.2 volts, and this is caused by the VC sat, or the saturation voltage. So in summary, the NPN BJT can be used as a switch, but it cannot perfectly pull down the output voltage or its collector node down to 0 volts. And if we want to add a switch near the supply, then what we actually need is an or a PNP BJT. So NPNs, when used as a switch, are normally at the lower portion of the circuit. However, PNPs, when used as a switch, are normally on the upper portion of the circuit near the supply. And ideally, or when the PNP is open, then the output will be exactly, say, 0 volts. So for example, we have an PNP or a switch above. If it is open, then V out is 0 volts because there is no current through this load resistance, just like here. But when the PNP is on, ideally the output must be equal to the supply voltage, but because of the VEC sat of the PNP, it would be approximately a bit lower than the supply voltage. So if VEC sat is 0.2 as well, then in this configuration, the output will be 4.8 volts. Now, what is an example where we can use this setup or similar to it? For example, we have a microcontroller that gives us a digital 0 and 1, for example, 0 and 5 volts, or possibly 0 and 3.3 volts, 0 or 2.5 volts. Then we can use a similar setup like this. So for example, you have a pin that outputs 0 volts or 5 volts. If you use this setup and, for example, add an LED, so when the input is 0, this is not forward biased, there is no current, so there's also no current, and the LED will be off. However, when the input is 5 volts, then the BJT will be on, and when it operates under saturation, then this node here is pulled down to around 0.2 volts, and there will be current through this LED, and therefore it will be on when the output is 1. So given that the microcontroller outputs 0 or 1, we can control if the LED is off or on. Now this resistor right here is necessary to, for example, get the excess voltage. So when the BJT is on, this is 0.7, this is 5 volts, so this resistor here gets the 4.3 volts. And aside from that, this also limits the current that is drawn from the pin. So for example, you have a limit on the amount of current that can go out of here, then you can design the value of this resistor. This resistor also acts the same. It limits the amount of current through this LED, so we can control the brightness. And also this one enables us to design such that this BJT right here will be in saturation when the input voltage corresponds to a digital 1. Now let's look at circuits where the BJT, or in our case, in our examples, the NPN is used as an amplifier. In this kind of circuits, the BJT is operated in the forward active region. And in this specific example, we are taking the output at the collector node. Let's say we provide input through the base, although this input supply voltage is not actually not the input we're referring to. We can use the circuit by, for example, adding a capacitor at this node and providing some input signal. Now, this input AC signal can pass through the capacitor and will cause a small change in the base voltage, which will cause a change in the current IB, and the changes in current IB will be reflected in the output since we have for forward active IC is equal to beta IB, and since beta is greater than 1, then the current here will be much greater than the one caused by this input, and therefore we expect that the output will be much larger. Now we'll not delve into the details on how this amplification works. What we'll focus only is how the DC biasing works, since this DC biasing also actually influences the amount of amplification that can be achieved, and also the DC bias must also ensure that the transistor is in the forward active. Now for this problem, let's say we are tasked to derive V out in terms of the circuit component parameters, assuming that the BJT is in the forward active mode. So since we are assuming that the BJT is in the forward active mode, we can fix the VBE junction voltage to be some VBE on, and again in the forward active case we can set, or we have IC is equal to beta IB. Note that even though we have defined V out in this node, we are actually analyzing it without anything connected in this branch. So the current here is the current here, and so this whole current here is IC. Now shown here from KVL at the base emitter loop. So this is the base emitter loop, although to close the loop we need to pass through this supply voltage VCC. So the voltage here is VCC and can be imagined to be provided by some DC voltage source VCC, which is connected with respect to ground. And when we say the base emitter loop, we're actually referring to this one, since this one is connected. So the voltage drop here, VCC, is equal to the voltage drop here, which is IBRB. So note that the IB is rightwards here, so IB is in this direction, and therefore the voltage that will appear across the resistor will have this polarity, and therefore by KVL or summing of voltages, this is RBIB plus VBE on, and solving for IB we get this VCC minus VBE on over RB. Now, at the output side, we can set up a KVL equation at the CE loop. So this CE loop is through the collector and emitter, and since these are both, let's just say, some supply voltage, they can be imagined to be shorted, and our KVL would pass through this loop. So VCC is equal to the voltage drop here, which is based on the direction of IC, will have a polarity of this one as shown. So RCIC plus this voltage here, which is VCE. Now this VCE is also actually V out, so we can replace VCE by V out, and when we isolate this we get VCC minus ICRC. Now using the fact that at forward active IC is equal to beta IB, then we can rewrite this as V out is equal to VCC minus IC, which is beta IBRC, and then IB is actually equal to VCC minus VBE on over RB. Now with this, knowing the supply voltage and the beta VBE on, we can actually um, design RC and RB to put V out on a specific voltage level that we want, which is most of the time around the middle of the supply range. And then we can also choose RB and RC to control the currents in the circuit. Another thing, we can also design V out such that we can ensure that it is in the forward active region. So this V out must be greater than VC sat. However, unfortunately, this beta right here is actually not very easy to control. So for example, you have a bunch of transistors in the lab, then you would normally expect that the beta of each transistor would differ. And so slight changes with beta may cause the V out to go out of the range that we want. And in the extreme case, can cause this BJT to be in saturation. So in some circuit design, the circuit is actually modified a little to make the circuit less sensitive to changes in beta. Okay, however, IB is easily controlled since this is approximately VCC minus VB1 over RB. However, when we convert that to IC, that's where the problem is. So IC is the one that is a bit hard to control. So to achieve a more stable DC bias point, what you can do is to add an emitter resistor and get this emitter stabilized bias circuit. And so let's analyze how this resistor actually helps to stabilize the circuit, the DC bias point, despite possible variations in beta. Again, we're assuming that this NPN BJT in our amplifier is in the forward active region. So again, KVL at the VBE loop. So VCC is equal to IBRB plus VBE on. So the voltage polarities are in this manner. Plus VBE on plus IE RE. Now, since IC is equal to beta IB, and we have the base current going in, collector current going in, and emitter current going out, then by KCL, current going in, IB plus IC is equal to IE. And so this beta IB is IC and 1 times IB is IB. So when we isolate so we replace this with IB times beta plus 1, and when we isolate IB, we get VCC minus VBE on over RB times, or plus beta plus 1 times RE. So from this one, we analyze then the other side of the circuit. So VCC is equal to RCIC plus VCE. So plus VCE plus IERE. So VCE is equal to VCC minus ICRC minus IERE. And we want this one to be greater than VCE sat. However, note that for this circuit, VCE is not anymore V out, since V out is with respect to ground. So actually, V out from here to here is VCE plus IERE. Or we can actually also use this other side, since the voltage drop here, ICRC, must be equal to VCC minus Vout, and therefore Vout must be equal to VCC minus the voltage dropped here, which is ICRC. So if we start from this point, Vout is equal to VCC minus beta IBRC. We replace IB with this equation here. Then we'll end up with this one. Vout is equal to VCC minus beta VCC minus VBE on over RB plus beta plus 1 RE times RC. Now this expression here is only dependent on the supply, the turn-on voltage, the resistor values, and the beta. Now how come this one is better? Now, since beta is large, even if beta would change by a little bit, it would still remain to be large, and this beta here and this beta here must be exactly equal. Now, if beta, for example, is very, very large, by L'Hopital's rule, what will be left with will be, say, VCC minus VBE on over RE times RC, which is not anymore dependent on beta. Meaning, if beta is sufficiently large, then even if it changes by some value, as long as it is large, then this circuit's DC bias point Vout is approximately maintained. Now, another way to bias the NPN in our amplifier is with the use of resistor dividers instead of only one resistor. So if we do the same analysis, then we'll have more loops and actually need to perform KCL at this point to analyze the circuit, and which complicates the analysis. However, we can somehow simplify that by getting the Thevenin equivalent circuit of this voltage divider. So the circuit can be analyzed much easier by finding the Thevenin equivalent circuit of the resistor divider first. Now, as a review, the Thevenin voltage is the open circuit voltage. So assuming that this thing here is not connected, what is the voltage here? And that is exactly VCC times R2 over R1 plus R2. Now, the Thevenin resistance is the resistance seen across these two nodes when the supply is turned off. And when we turn off the supply, say we have this original VCC, but when we turn off the supply, meaning VCC becomes 0, it actually acts like a short circuit when the voltage is 0. And thus, from this point relative to ground, what we see is a parallel R1 and R2. And therefore, we can just analyze this whole circuit as this circuit with this Thevenin equivalent. Now, we won't need to do KCL anymore, and so this thing here is much easier to analyze than this one. Although in the end, we need to convert RTH and VTH with these values. So if we actually perform the conversion and now do the same, which is to derive Vout, we can again start with this loop. So VBE on is right here, and by KVL, VTH, the drop from here to here, must be equal to the drop from here, but going through here. So VTH is equal to IBRTH plus VBE plus IERE, and again, IE is equal to beta plus 1 IB, and isolating IB, we get this expression VTH minus VBE over RTH plus beta plus 1 RE. Now, the output side, again, this is VCE. So VCC is equal to ICRC plus VCE plus IERE. And isolating VCE, we get VCC minus ICRC minus IERE, which we want to be greater than VCE sat. In terms of output, voltage, Vout is equal to VCE plus IERE. Or it is also equal to VCC minus ICRC, where IC is equal to beta times IB. So changing this or substituting this IB with this expression, so we get this and get a very similar expression, although instead of the VCC term here, we just end up with VTH. And since we still have this beta at the numerator and beta at the denominator, then this circuit is still quite stable even with changes in the beta value. Now, this circuit right here uses only a single resistor, is still stable in terms of its bias, DC bias point, but this time with the use of this RB from the collector terminal to the base terminal, this circuit actually is easier to ensure that it is in the forward active region as compared to the previous circuits. And why is that so? We are actually sure that this circuit right here will be in forward active regardless of the values of the resistances, as long as the supply voltage is large enough. Now, how come the circuit is able to achieve that? So note that we want for forward active that VCE is greater than VCE sat, and that VCE appears at these two terminals. Now, since this is the supply and the current can only go from supply, a positive supply down to ground, the current can go also from this point to this point, then we are sure that this one is approximately VBE on, as long as this one is slightly greater than VBE on. So this one is approximately VBE on already. Now note that as we have mentioned, the current can only flow down the circuit, and with that current direction, then we'll have this current IB right here, and with this we are sure that there is some voltage drop across this resistor RB. Now that voltage is actually equal to this voltage as well, which is VCB. Okay, and now by KVL, this VCE right here, which we want to be greater than VCE sat, is also equal to VCB plus VBE on, or IBRB times VBE on. Now writing that, we get this equation right here. VC is equal to VBE on plus VCB, which is IBRB. Now we want this to be greater than, say, 0.2, but this one is already 0.7, and this one can only be positive, and therefore we are sure that as long as this junction is on, then VCE is greater than VCE sat. Now, in deriving the output voltage, we can do the similar approach. So we do KVL passing through the BE loop, So from this point to this, to this, to this, back to ground. So VCC is equal to I1 R1. So let this be R1. I1 R1 plus IB RB plus VBE or VBE on plus IE RE. And let's say we isolate I1, which is the current here. Now note that this I1 is not IC. Since by KVL here, what we have is I1 will split into IB and IC. Although that current is also actually equal to IE, since IB plus IC is equal to IE. So I1 is just equal to IE, this I1 here. And since IC is beta IB, I1 therefore is equal to beta plus 1 IB. So this one can be written in terms of IB. This is in terms of IB. This is also beta plus 1 IB. And solving for IB, we get VCC minus VBE on over RB plus beta plus 1 R1 plus RE. Now, KVL passing here, VCE, then VCC is equal to I1 R1 plus VCE plus IE RE. Solving for VCE, isolating VCE, we get VCC minus I1 R1 minus IE RE. Although we're most likely sure that this one is greater than VCE set already. Now solving for Vout can be written as VCE plus IE RE or VCC minus I1 R1, although I1 again is IE or exactly equal to IE. And since this IE can be rewritten in terms of IB, then we can write this equation. And substituting IB with this expression here, we'll get VCC minus beta plus 1 IB, which is this term, times R1. Now, since we still have this beta at the numerator and beta at the denominator, then again, the circuit is still stable despite of possible changes in beta, as long as beta is quite large. Still, I'm considering the context of this whole denominator right here. Okay, so now let's have some numerical examples. Consider this fixed bias circuit right here with an NP and BJT. We will use the normal values of 0.7 for VBE on, 0.2 for VCE sat, and we'll assume a beta of 100 for this transistor. Now the task is to determine IC for RB is equal to 2 mega ohms. So this must be 2 mega ohms. Again, we'll start with a forward active assumption, and given that this must be VBE on, and therefore IB must be equal to the current through this RB directed rightward, so 3 volts minus 0.7 over 2 mega ohms, and we can compute 1.15 microamperes. And since we are assuming that it is in the forward active, we'll proceed with using IC is equal to beta IB with beta is equal to 100 and get this 115 microamps. Now, in terms of the problem, we already have a candidate answer, and we'll still have to verify if that's the case, if the BJT is indeed in the forward active mode. So we need to get VCE. So by KVL, at the output side or at the collector side, okay, so here we have the voltage across RC, VRC is equal to 10K times IC, So current is downwards entering the positive terminal. And using this 115 microamps times 10K, we get this 1.15 volts. If this is 5 volts, this is 1.15 volts, then this must be 3.85 volts. And that is VC, which is also equivalent to VCE already, since VE is 0, since the emitter is grounded. So VC is 3.85, and since this VCE is greater than 0.2 volts and IB is greater than 0 as well as IC, then the NPN is indeed in the forward active region, and we can say that this is IC for this example. Now, instead of 2 mega ohms, let's say we change RB to 100 kilo ohms. So from 2 mega ohms, we change it to 100 kilo ohms and check the changes in the circuit's operation. So again, to get IC, we start with IB. IB is equal to 3 minus 0.7, since we're assuming it is in the forward active, over 100K. That's 23 microamperes, 2.3 volts over 100K. Again, beta is 100, so IC is equal to 100 times IB, or 2.3 milliamperes. Again, we still need to verify if the BJT is in the forward active region. VRC is 10K times IC, which is 2.3 milliamperes, which gives us 23 volts. VC, the voltage here, VC, with respect to ground, is 5 volts minus the drop here, which is VRC. So 5 minus 23 is negative 18. And since VC is equal to VCE, then this is negative 18 volts. And therefore, we get IC and IB greater than 0. So okay, but VCE is not greater than VCE sat. It is actually less than VCE sat. So negative 18 is less than 0.2. Then the NPN BJT must be in saturation instead of the forward active. And we must redo the analysis. Now, if the BJT is in saturation, then we'll just replace this with VCE sat. And note that we cannot anymore use IC is equal to beta IB. However, this one should suffice in identifying IC. So IC is the current through the RC. And if this is 0.2 or VCE sat, then the current here must be 5 minus 0.2 over 10 kilo ohms. So 4.8 over 10K, 480 microamperes. Now, IB is still 23 microamperes, since this is still 0.7 even in saturation. However, we again cannot use IB is equal to IC over beta. So instead, this remains at 23 microamperes, and since IB is greater than 0, IC is less than beta IB, so 480 microamperes is less than 2.3 milliamperes, which is the case if the BJT is in forward active mode. Then the NPN BJT must indeed be in saturation, and therefore what we should answer is this one. Now, if instead you are tasked to analyze the same circuit but you are given some IS value, then we cannot simply assume that VBE is equal to 0.7, but rather we'll have to solve VBE in our equation. So we'll just write this in general as some VBE. and use the equation IC is equal to IS EVB over VT minus 1 times 1 plus VCE over VA. Although in this case, we are given that VA approaches infinity, so something over infinity or some finite value over infinity, this must be approximately 0. So this whole factor here will just be equal to 1 plus 0 or 1. So we can actually remove that already. Now, this equation was actually under the assumption that the device is in forward active. And proceeding, we can solve for, say, IB. From this side of the circuit, we have 3 volts minus IBRB minus VBE is equal to 0. Now, since we are assuming that it is in the forward active, then IC is equal to beta IB, and IB is 1 over beta times IC. But IC is equal to this equation here. So IB is equal to 1 over beta IS e to the VB over VT minus 1. Substituting this IB expression in this equation, we have 3 volts minus 1.6 femtoamperes over 100 times e raised to the unknown VBE over 0.026, assuming that this is in room temperature, minus 1. So that's IB times RB, which is 2 mega ohms, minus again the unknown VBE. So in this equation, we only have one unknown, VBE, and using our calculus to compute this equation, we'll get VBE to be around 0.6505 volts. Now we can use that VBE value to substitute here and get IC. So IC with VBE is equal to 0.6505 can be computed to be 117.47 microamperes. And to verify if it is indeed in the forward active, we need to solve for VCE. But VCE is simply VCC minus the voltage drop here, which is 10K RC or RCIC. So VCE is equal to 5 minus ICRC, but we know RC is 10 kilo ohms, and therefore we can solve for VCE, and this will give us 3.825 volts. Now, since IB is greater than 0, we have solved it, or actually, since IC is positive, then IB is also positive, since we'll just scale it by beta, or 1 over beta. And VCE, 3.825 greater than 0.2, then the NPN BJT is indeed in the forward active region. And therefore, we can say that this is the final answer. Now, we present here an alternate approach to solving the circuit, still using the IS value. So in the last equation, we actually solved first for VBE before solving IC, but in this approach, we can actually solve in terms of IC. So instead of setting up the equation in terms of VBE, we can actually solve for IC. And from this original equation, we can solve for or isolate VBE. So IC over IS plus 1, we ln that and multiply by VT to get VBE. So this equation right here is actually the KVL equation at this part. So 3 volts minus IBRB, but IB is just IC over beta times R, so multiplied by RB, minus VBE, but VBE is VT ln IC over IS plus 1 is equal to 0. And with this, we know IB we know beta, we know RB, which is 2 mega ohms. VT is 0.026, we know IS, and the only unknown here is IC, and therefore we can solve for IC and proceed with the analysis from there on. Now, we give here a note that either way, whether we solve it in terms of IC or VBE, do not assume that VBE is equal to VBE on, and actually there is no VBE on indicated here when using this equation. And why is that so? Normally, this term here can be can have a small effect only on the IS value, IC value. Most of the IC is dependent on this VBE term here. And if we assume that VBE is equal to 0.7, then this is already fixed. And since IS is constant, that would mean that IC is always constant regardless of the values of the resistances or the voltages in the circuit. And therefore, you should not use VB is equal to VB on with this equation. So if you're using this, do not use this. If you are using this, do not use this one. For our second numerical example, say we have this emitter stabilized NPN circuit using these values. So we're not using IS. Determine RB, RC, RE, VC, and VBE given that the supply voltages are this, and these are the IC and the collector and emitter voltages. Now, assuming that the BJT is in the forward active mode, and why is that a good assumption? So note that this is 12 volts and this is ground, and therefore most likely this base emitter junction can be forward biased by 0.7 from the given. And aside from that, given that the collector is at 7.6 and the emitter is at 2.4, then VCE can automatically be, or can easily be computed as 7.6 minus 2.4, which is 5.2 volts. And that is greater than VC is at, which is 0.2, and therefore we're actually kind of sure by this point that this NPN BJT is in the forward active. So using IC is equal to beta IB, we know IC from the given 2 milliamps. So IB is simply 1 over beta IC. Beta was given to be 100. So 2 milliamps over 100 is 20 microamps. So we can say that this is 20 microamps. And by KCL, 2 milliamps plus 20 microamps is 2.02 milliamps. So we already know all the currents and voltages in the circuit. We can now use Ohm's law to determine the values of the resistances. So RC is 12 minus 7.6. This voltage here is with respect to ground over the current 2 milliamperes, and we'll get 2.2 kilo ohms. Now RE is 2.4 minus 0 over 2.02 milliamperes, and that is around 1188 ohms. VB, the voltage at the base with respect to ground, can be solved as 0.7 plus 2.4. So that is 3.1 volts, and the resistance RB is 12 minus VB, which is 3.1 over 20 microamperes, so 445 kilo ohms. So again, VC is 5.2, and since IB and IC is greater than 0 and VCE is greater than 0.2, then indeed the NP and BJT is in the forward active region. And we were able to solve our B, our C, our E, VCE, and VB. For example 3, we have this resistor divider biased emitter stabilized NPN circuit, and the goal is to determine the currents IB/IC and the voltages VC, VC, VE, VB, and VCE with this resistance values. So again, to analyze this in a more simpler way, we can start by converting this divider into its Thevenin equivalent circuit. So the Thevenin voltage is 16 volts times 9.1K over the sum of 9.1K and 62K, and that is around 2.04782 volts. The Thevenin resistance is the parallel of the two, and that is around 7,835 ohms. Now the rest is not anymore shown, but the final answers are provided for you to practice on your own and verify your answer. So hopefully you'll be able to get these values eventually. And since it is already given in this slide that it is in the forward active region, since IB/IC is greater than 0 and VCE is greater than 0.2, then you can start with the forward active assumption without worrying. In this last example, we have this emitter stabilized NPN BJT circuit with VBE on, VCE sat, and beta values given. Now the task is to determine the range of RB. So RB's value is unknown, although this RC and RE values are given. The range of RB that will operate the transistor in saturation, also with this supply of 12 volts. So to approach this, what we can actually do is to assume that the device in the forward active and check when we will not meet the condition that VCE is less than VC sat, since if this is not met, then the device must be in saturation, since we are sure that with this supply voltages that the base emitter junction is forward bias. So the only question is that is the collector base reverse or forward biased. So we're only left with the option of forward active or saturation. So we can assume that it is in the forward active and check when the condition will not be met. So since we are assuming forward active, we can use IC is equal to beta IB, and VBE is exactly equal to VBE on, which is given to be 0.7. And so with proceeding, IB is equal to the current through this resistor. The voltage across it is 12 minus 0.7 plus beta plus 1 IB. So we'll multiply RE by beta plus 1 eventually and divide by the resistance values. So this one is actually quite a shortcut, but this should hold true. And it is also actually quite interesting to note that since we are adding RB and beta plus 1 RE, then at the point of view of RB, it sees a resistance that is beta plus 1 larger, which is actually, we can get this same equation here if this RE here was not there and was here instead, but beta plus 1 times larger. And that is also one of the reasons why we are calling this device a transistor, since it is able to transfer the resistance in effect. Although, of course, this circuit is not equal to the original circuit, but from the point of view of RB, it sees a resistance that is beta plus 1 larger, and um, on the other end, this 680 ohms resistor actually sees a resistance that is beta plus 1 smaller. So if we remove this and make this RB over beta plus 1, then we'll get the same KVL equation through this loop. Although we'll not anymore elaborate on that. Okay, so we basically have that equation with IB isolated, and we can multiply by beta, which is 100, to get IC. And then since we want to get the range where VCE is not greater than VCE SAT, or VCE is less than VCE SAT, then we need to get an expression for VCE. VCE here is equal to the supply voltage, 12 volts, minus the 2 voltage drops here, which is RCIC and IERE. So VC is basically equal to 12 volts, this time in terms of IB, RC times beta, and RE times beta plus 1 to be multiplied by IB. So we have this expression here for VCE, and we need to get the range such that VC is less than VC SAT. So VC is this whole term here, minus which must be less than 0.2 for it to be in the saturation region. And substituting IB with this expression right here, and moving values or terms. So we move this 0.2 here, so 12 minus 0.2. We move this whole term here to the other side, and this becomes positive. To isolate IB, we divide this whole term here. So we have this beta RC plus beta plus 1 RE is less than IB. However, IB was equal or is equal to this expression right here. And since we know RE, we know RC, we know beta, and we're only left with one unknown, RB, then we can actually isolate RB and get the valid range. So here we get RB to be less than this value to ensure that the transistor is in saturation. Or if we use RB less than this value, then we'll expect that this transistor will be in saturation. So if we want it to be in the forward active, then we'll just use RB greater than this value right here. Okay, so in summary, we have introduced this model equation, which we will somehow derive in the next lectures or lecture. And this is only applicable in the forward active region and can be used alongside IC is equal to beta IB. Now, to verify if you can use it, we must check that VC is greater than VC SAT, and a good or ideal BJT has a VA approach that is very, very large. And if it approaches infinity, then this term right here technically vanishes, and we'll only be left right with this equation, which tells us that IC is not anymore a function of VCE. And that's why when VA approaches infinity, the plot is technically flat in the forward active region. So changes in VCE does not result in a change in the value of IC. However, if VA is finite, then we'll expect some increase in the current here as VCE increases. Now, this VA is called the early voltage and should not be confused with the applied voltage. And it is called early voltage because of the surname of the one who described it. We also introduced and used the following models in this lecture, specifically for NPN. We have this fixed or constant voltage source for VBE and current dependent current source for IC, but we must ensure that IC is greater than 0 and VC is greater than VCE sat. For saturation, we have two constant voltage sources, one VBE on and one VCE sat. The condition must be the currents must be positive, but IC must be less than beta IB, since this is the maximum current. Okay, and in saturation, we expect something less than the forward active current. In cutoff, the currents are approximately 0, so we replace it with an open circuit. And to verify if it is indeed in cutoff, VBE must be less than VBE on, so that this junction must not be forward biased. Now, the equivalent models for PNP or an example involving a PNP will be discussed in the problem solving slides. And that's it for this lecture. Thank you very much.